Last time, are you guys ready? Ready or not? Exponential functions, keep going. Last time we did one problem on exponential functions, and then you had one more in your quiz, but last time we actually learned what it means to have exponential growth or decay. Looks like this. P equals initial value P0 times the exponential function with K. K can be a growth rate or decay rate, and T is time, days, minutes, seconds, years. So we did one example. Example was, if you're investing money, that's your P0, initial value, and then they promise you 1% interest rate annually, T is in years, 1% was your growth rate as 0.01. Calculate this and that, and we did calculate this and that, including the speed. Speed was derivative. Let's do something more biological, which is very, very applicable idea of calculating the bacteria growth. And the labs that actually practice all of this, they have antibiotics. They're trying different antibiotics on different bacteria, and then they have testing one and original one, and they see that the growth is changing, decaying, stopping. So that is exactly what people do. They check the growth of the bacteria with antibiotics, without, with different one, with combination of antibiotics. They know it's exponential growth, they model it mathematically, and then practice it in the lab at the same time. And the data should match math. So I don't want to throw at you the idea that the bacteria spread is exponential function or exponential growth, but you have to say, like, is this linear to you? No. Linear functions is like your age. Today you're 21, in a year you will be 22, in a year you'll be 23, and it will be weird if you become 40 next year. So that means your age is the best example of linear growth. This is crazy exponential growth. From how many did we start? Let's see at the beginning. 3. From 3 bacteria, it occupied the whole territory in a couple seconds. That is pretty impressive, and that's what we call exponential growth. So I have one more to show you, which is this one. Pretty cool idea, and it's exactly what I see when they. You don't want to? Okay. It's exactly what I see when they present at the conferences. How does it all look like? Oh yeah, I had this one over here. At the conferences, they present these, and mathematically they explain how they use. On the left-hand side, let's see. See? How they introduce the bacteria on the petri dish with food, without food, and then they make experiments like here, turning on or turning off some kind of procedures, either genetic mutation or adding antibiotics or combining several together. So, let's answer some questions. For example, let's find the continuous growth rate K. That's only the first question. We'll have many questions here. But for now, write down, suppose there's a population of bacteria is growing exponentially. Initial time 0, so we start exploring this bacteria growth at time 0. And when you looked at your petri dish, you saw 150 bacteria. So you counted it. Or you introduced to the petri dish 150 bacteria. You waited for 2 hours, and then you saw 220. This information is enough to build a model. As you can see, I don't see any equation. You, as a modeler, as a biologist, lab scientist, you will be required to build it yourself. But since you know it's exponential growth, it says that actually. That's its important phrase. That phrase gives away the whole idea. If it says growing exponentially, now you know it should be one of the formulas which we're going to teach you. For now, we only taught you one. P equals initial number of whatever started there, money, profit, bacteria, number of rats in the rat lab, times E raised to the growth or decay rate, K. If K is negative, it's decay. T is time. In this case, hours, I guess. So let's figure this out. This is what I just made up right now. You see, I'm modeling this, knowing typical equations. That's exactly what people do for the master's degree and then harder stuff for PhD. They model things from the equations. So let's write down for A. First of all, let's plug things we know. I don't know what we know. What should we plug? What do you think is given here? What do you think is, let's say, I would ask it this way. What do you think 150 is?
P0.
P sub 0, how can you justify? It says initial population. Thank you. It is initial population. Usually called IV, initial value. So that's initial number, I. That's going to be my P0. Then, don't touch E is E, so that should be fixed. Anything else can be given or not. What is 220? P, right? It says like in 2 hours, P became 220. So this is my P, but when? In 2 hours. How would I write down 2 hours? T equals 2. Very interesting. So the general model will be first, P is the result of which I will see in T time. T is the input I'm feeding time. P is the explosion of the bacteria growth. Original number of bacteria was 150, and then this 150 is multiplied by the positive exponential function. Well, exponential function is always positive, but growing exponential function with the rate k, which we don't know, multiplied by time t. So that's going to be a general model from which we will be looking at things now. With, I would say it's even not A, it's just in general. I will see 4 hours. Yeah, that's actually in general. And now A gives you different information. A says, well, actually, when I waited for 2 hours, I saw that P of 2, well, you don't have to write it down yet, became 220. 220. Bacterias, let's call it B. So they ask us to find what?
K.
Find K, exactly. And K doesn't have units, by the way, it's a rate. 1% was in business model, this might be something different. So K is K rate, whatever it is. Now, can we do it? Let's see. This is what's given, this is what we need to find. Let's put it in the model. P is 220, that's left-hand side, equals 150, that's the same number we used to have, times E, K is unknown, but time is 2. So this is what we got from the red box. Original value, now we have new value, and we have time 2 hours. Because P at 2 gave me 220. I'll go away, this B. And then hours, kind of, yeah. Maybe put it in parentheses, hours, bacterias. We want to solve for K. Solve for rate K, it's rate. And that's actually exactly how people, rate is the most important part in those problems. When the COVID started, the rate of the growth of the people who got sick was important to know if it's pandemic or epidemic or local, some kind of disease. But how to find K? You have initial people who got sick, you waited a little bit, hopefully not too long. Now you have new number of people who got sick. You plug it just like we did, and you said, okay, we started with 2 people with COVID. Now we have 1,000, and it took only 1 week. Plug it in, find the rate, publish it, and in the news they will say, wow, the spread rate actually matches the model that is called epidemic model or pandemic model. So that's exactly how people do. They collect data. So the data collected tells me that 220 was in 2 hours. How would we find K? You know my idea. Isolate e to the k times 2. In this case, to isolate, I will divide by 150 to both sides. 220 over 150 equals e to the 2k. Isolating exponential function. I did that. How to dig K out of the exponent? Any ideas?
Natural log.
Natural log, ln, thank you. So you know it, you see? Now when you see this in the model or in the news, you know how they did it because now you took this class and you know how it works. Apply log to the both sides. In this case, ln will be nice. And you will have natural log of 220 over 150 equals ln under e, so it will be 2k, thank you. That's how you dig it out from the exponential function. But I need k, I don't need 2k. So let's divide by 2 and write down k equals a fraction and natural logarithm of 220 over 150 over 2. Which some kind of number you could actually write down as 1/2. What kind of number? First of all, it is positive. Logarithm function is always well, actually not. Logarithm function is positive because 220 over 150 is positive, greater than 1. And you divide it by the positive. So the rate is indeed positive. It's 0.195. It would be wrong if you get negative number in this case. Then you will call it exponential decay, like chemical decay. Chernobyl blew up. Now there's like lots of chemicals digged into the ground of north of Ukraine, and they calculating this radioactive decay using exponential functions. So in this case it says exponential growth. It should be positive in this case. That's why it's called exponential growth. That is my k. When we found this k, we now can complete the model. P now equals P sub 0 is still 150. That's the initial number of bacteria. Now it's multiplied by exponential function with the given rate which we found. Approximate or exact? Let's have exact. Approximate. 1915 T. Now it's our new model. I like exact answers actually, but it's fine. 0.1915 is more visually explanational. What does it do? Still less than 2, 0.2, but it's pretty big. It's pretty big. Ask me, what do you think about this? Before we do question number 2. Not too bad? And it is pretty interesting because it's exactly what people do in science. Second question, B. So you're kind of following the footsteps of scientists hired by CDC to calculate all of this stuff. Find the population at t equals 4 hours. Find the population at t equals 4. I need to restart. T equals 4. Population. That's you. At t equals 4 what? Hours. Units hours. Now when we found rate, that was the most important part, to be honest. When you found the rate, now you can find anything. You can find in t equals 1 million, 1, 4, 0, whatever you want. So that is the easy one. You just do what? You plug your t, which is 4, into the model you just created. 150 was the original number of bacteria you started with. It is keep growing because it's multiplied by the exponential function with growing rate, which we just discovered. But instead of t, I will have 4. So we're waiting for 4 hours and see how it goes. Grab your calculator. Not right now, you don't have to. I will tell you the solution, but you grab your calculator or a computer. The more decimals, the better, the more precise it is. And you don't get half bacteria, it is weird. So you round it to 322 bacteria. So we start with 150. In 4 hours, it's already 322. That's a very good result. Bless you. Very natural question is question C. When the population reach something. When will the population reach some kind of number? Reach 500. Any number. Last time we had it doubled. We can have triple, we have 500, anything you want. Usually this number means something in scientific ideas. So 500, it's like the moment you need to apply antibiotics, or the moment your body starts getting high temperature, and so on. Or the moment the immune system actually has an immune response. What do you think I should do now? Let me, okay, Chris, you can.
Almost the exact same thing you did the first time.
Well-
You just solved for t instead of for k.
Yes, so 500 is what?
500 is p.
P, so what should I write down?
500 equals 150 times e 2.195.
150. 150 is initial population. E, rate we found. And now T is unknown. How do I know? Because this when question means find T. When 500 is a given output. Does it make sense? So we try to teach you as biologists to read words and then create math out of this. Math or math. And create mathematical equation out of this and then learn how to use it. Now we dig out t out of the exponential function and the whole process repeats. Isolate exponential function by dividing by 150 e to the 0.1915t equals, now it's 500 over 150, which you could simplify. Apply log to the both sides. ln undoes e, so it's now 0.1915t. That's exactly why we're doing it, because we want this exponential part go down. That's why we're applying log to both sides. But now it's going to be ln of this fraction, 500 over 150. Finally, dividing by this rate or whatever is attached to t will give me t. So t equals 1 over 0.1915 ln of 500 over 150. And you usually calculate this number approximately at the very end. If you do approximate calculation in the middle, it will mess up the last answer. So we always recommend to find the exact formula first and then use the calculator to approximate this formula. If you do intermediate approximation, the error will be accumulated and the last answer will be way too off. But this number tells me that it is 6.29 hours. 6.29. Oh, good job. So we need to wait for 6.29 hours to get 500 bacteria for our experiment. That's the idea. There's only one important question we did not answer. Well, there's so many questions we can answer. How it responds to light, the equations for that. How does it respond to antibiotic, this amount, this amount. I will show you later, I mentioned before, Harvard video for the bacteria. I'm waiting when we start to learn entire derivatives. Then you will see how amazing the growth rate is, how the area can be accumulated, and how bacteria actually occupy the territory. It's a pretty cool idea. But there's one more question left to answer. How fast? What does that mean? Derivative. That's why we are learning it. How fast is the population increasing? Is the population, let's call it pop, increasing? We actually don't have to call it increasing. Derivative should be positive. That means it's increasing. So we can say changing, but it's fine. First at t, so at any time. And then also at 3 hours. How fast is a synonym of derivative? See, they want us to go to the very beginning, the red box we had. When I wrote p equals 150e, I could keep k. K is a constant, so it will not change the process of differentiation. But I found it, so why not put it there? 0.1915t. This is the red box. But to be honest, when you differentiate, k is a constant, so it will be just general anyways. And they ask us to find p prime, which checks your chain rule abilities. Oh, why do we learn the chain rule? That's why we learn chain rule. We teach you chain rule exponential functions to find these important things. So 150 survives because it's multiplied by e. And moreover, it is called rate of change. So 150 was initial value and now it's changing. E should be copied because derivative of e is e. Right? So derivative of exponential, that's your homework. You should check it out. It's pretty fun. Exponential function gives you exponential function when you differentiate. But in times, chain rule says chain rule says, don't forget to differentiate the function inside. And inside, it means the exponent. Derivative of that function is 0.1915. So the rate jumped out when you differentiate. That's a pretty interesting idea. Rate will be multiplied by 150 now. And then you can calculate the answer. Well, this is the answer in general for the derivative for any t. So it's p prime of t. And then they ask, what is p prime at 3? So you plug carefully 3 into the time of your derivative. T is 3, but at your derivative. And then you can say, oh, it's actually approximately at 3 hours, the rate of change is 51 bacteria per hour. Bacteria per hour. Remember that derivative has units per or slash. Bacteria per hour. So at that moment, every hour gives you 51 bacteria. It's quite a lot. But it does change at every moment. So to explain this phrase, it means 3 hours later, 3 hours later, the population is increasing. As you can see, it's positive, right? So increasing. The population is increasing by or at, let's do at, 5 bacteria per each hour. 51, thank you. 51 bacteria per hour. That's what it means. So at 3 hours, we found the number before. At 3 hours, it was 4. That's fine. At any hour you can plug in, you'll get exact number. But for derivative is, okay, so what is the change at that particular moment? It is exponential function after all. It actually looks like this. I should show you because some of you are visual learners, so I think it's healthy if you know how it looks like. Last time I showed you this, you literally open any graphing calculator you have and you plot P equals. We start with 150 E, and then we found this rate K. What is it? 0.1915. When we plot it, it looks like this. Very typical graph, to be honest. You barely see the difference with the previous one. So what we found is that at 3, it's over here, the slope is positive, and when you plug here the number 3 into derivative, into the slope, you will get 51. But the thing is, it will be much bigger number at later time. If you wait for, so here, at 3, we found the tangent line, the slope M at 3 was 51. But the thing is, over here, it will be much bigger number. Over here, it will be much bigger. The bigger and the more positive, the more speed is increasing. That's what derivative is about. That's kind of the idea. Here's the graph for you. Looks like little worms climbing. Like so. Derivative. Slope M. That's what we did at 3. So that's your exponential growth. Very interesting. What do you think about that? Interesting or not? I mean, that's exactly like, I think many of you will be doing it. In general, maybe as an internship or as a full-time job. So, logistics models. They fix math a little bit to be more realistic. Logistic growth model. Logistic growth model, I already mentioned last time and I asked you this question and you were smart saying, yeah, we got it. We got the idea that in real life, bacteria will not be growing like this forever. In real life, there will be a limit of the space, resources, and food. So it will be stuck. It will stuck. There's not infinitely many resources on this table. Bacteria first will blow up and then it will reach the edges and slow down. So that is actually the difference between the graph, which we just learned recently, waiting t hours or days or whatever t is. P is the result of the population. P0 is the initial population and it's not 0. We should start with at least 2 rabbits to see how they grow in a population. We should start at least with 1 bacteria to see how it divides. Then the exponential function grows, looks like that. And we said, oh, this is the model we call exponential growth model, starting with the original value, P sub 0, EKT. That's exactly what we just learned. At 0, you plug 0 into t, it gives you P sub 0. This is the graph for the exponential growth model. So this is, we learned already, exponential growth model, not the logistics one yet. And in this graph, as you can see, we learned limits for a reason. When t is going to the right, to infinity, P of t is growing where? When t is going to the right to plus infinity, P of t is going where? Who knows? Who remembers limits? To plus infinity up, right? To plus infinity up versus right. That's your input versus output. T is going to positive to the right. Population is going up exponentially. That is not realistic. Not realistic. We cannot have infinitely many humans, even though we also grow exponentially. There is limited number of Earths to live in. And same with cancer, same with bacteria and rabbits and everything else. So that's why logistics model was introduced. Logistics model has some roof of this growth or stopping mechanism. It starts exactly the same. Let's start with P sub 0. Let the bacteria grow. So input is time, output is P. At 0, we have some initial value. It will be growing exponentially, just like before, like so. And then we're going to introduce a horizontal asymptote, which we're going to call L. Y equals L. Y equals L. It might never reach it, but it will be used as a roof or some kind of restriction. It will blow up exponentially and then it will be shrinking to L. It might never reach it. So we don't expect to have bacteria completely occupying the whole Petri dish. It actually knows the edges of the Petri dish and slows down the rate and waits for the previous bacteria to die, to eat them, and keep living. If it occupies everything, everyone dies. So living organisms, they know that they need to stop reproducing at some point. This one is more realistic because the population still can grow exponentially in the long run, and we're going to assume that as t is going to infinity, P of t is going where?
L.
L. That is more realistic. And L will be called carrying capacity. L is carrying capacity. This is actually a new term for me. I mean, I heard it many times. But to be honest, L is called so many different ways. So in this class, I decided to fix carrying capacity term. But in different books, they do mention different terms. Capacity. But it makes sense. Carrying capacity. Yeah, it makes sense. To call it this way, why not? So, in the long run, nothing should go to infinity. If we're talking about exponential growth of population and stuff, money, it shouldn't go to infinity. There should be some kind of limit, and that's what we're going to call carrying capacity. This is called logistics growth model. Logistic growth model, which is more logical. That it makes sense. When P is small, what is happening? At the small P over here, let me write down. When P, let's see, P, yeah. When P is small, so like over here and here and here and here and here, is small, it grows very fast, exponentially. It grows TH. exponentially. So derivative of p with respect to time is growing up. But when p gets too big or larger and larger, it's still growing. As you can see, it's not decaying or anything, but now it grows slower than before. So when p is large, so for example over here, for large p, as you can see, it's still growing. It grows slower. Growth slower. And that's why we taught you concave up and concave down cases, because it's exactly the second derivative matters here. First derivative is positive, means second derivative is positive. First derivative still positive but decreasing. Second derivative is negative, the sad face, if you remember. It's growing slowly, so derivative is going down now. Just a second. Yeah, this is the first one. I'm just mentioning the second one. And then to remind you about concavity. And then as t goes to plus infinity.
Oh, the second derivative is not negative, but it's going down.
Yes, exactly.
Sorry, that because
Then the limit as t goes to infinity, the population grows, now has a fixed limit. Remember, it might never reach it, but at least it's there, which is L, which we're going to call carrying capacity. Concavity, which I just mentioned, maybe confused you a little bit. This is my point of inflection. At this point, something happens. So the population was growing exponentially, blowing up. For example, rabbits in the Yellowstone were growing, there were no predators, and then something happened. Maybe they saw the limits, finally the limit of the forest. Maybe the predator was introduced. They would not stop reproducing, but now it's harder for them to do so. Less food, more predators keep killing them. They will still grow, but slower, because of the carrying capacity. Very interesting idea. So logistics model have different equation. And that equation is not as simple as before. And our job is to explain you carefully what it is. Now, P of t will be P sub 0, the original value, multiplied by the carrying capacity. That is because and. Product usually in math means and. So P sub 0 and the living capacity over, so that's going to be rate or a quotient, P sub 0 plus L minus P sub 0. What is the difference between the roof and the bottom? The bottom was P sub 0. Multiplied by E minus KT. As I told you, either K is negative or people put negative in front. So that will regulate the exponential growth. Oh, it says below, no need to memorize. Okay. No need to memorize. That's a good note. I did not know that. No need to memorize unless you take upper level classes. Then they will force you to memorize. But the idea is, if you remember limits, just kind of interesting, does this actually match what I just wrote? So limit as t goes to infinity of this function, supposed to give you L. Does it? So very interesting, I wanted to point this out. P sub 0 L, P sub 0 plus L minus P sub 0, e to the minus kt. When t is exploding to infinity. So from all of those letters, usually people complain the upper level of math you take, the less numbers they are, more alphabet is involved. That is what modeling is. If you take physics class, biology class, you'll see lots of letters there. They all represent something. In this whole formula, only this is a variable. One t, that's it. Not p, l, or k. Only t is a variable. Everything else actually is fixed. You literally mention it at the beginning of the article. For this scenario of rabbits, L will be 5 million. For the bacteria, 50 million. For P0, let's do 2 rabbits. So it's fixed. K is also fixed. With the limit, very interesting idea. Do you know that all this shrinks to 0? Why? Can you guess? You should know from the limits chapter. Who knows? Except Chris.
Sorry.
No, I'm happy that you know, but maybe someone else want to say. Why it shrinks to 0 when t is huge? Yes?
Because there's a negative.
Negative sign. This negative sign means e to the minus kt is actually 1 over e to the kt. Thank you. So this thing explodes to infinity, but 1 over infinity shrinks to 0. Make sense? Anytime you see a negative sign in the exponential function, you should know it shrinks when t is large. So the whole thing, just a second, the whole thing shrinks to 0 except the numerator, with p sub 0 times L over the denominator, which is p sub 0 plus 0. P sub 0, I will not do it like so. P sub 0 L over p sub 0 cancels, and it gives you L like we expected. That's what we expected. On the right, on the graph, as you can see, on the right, the logistics growth model actually shrinks up to the ceiling, which is L, which is carrying capacity. Yes?
Why doesn't e to the kt just move to the numerator if it's 1 over?
Because it's plus. If you have addition in the denominator, you cannot just put something up.
Oh, because it's not just multiplied. Because
Yeah.
it's multiplied by the whole
If it's
thing,
multiplied, yes, you could.
then I can just move it.
Good question, yeah. That's the idea. And a very nice example about fungus. Look at that. That makes sense because I'm not surprised that fungus has exponential growth, but fungus does have restrictions. That's you. So a fungus has been found on the island. That's a very nice, fun example. I like the chapter of exponential growth because American books, they like to do lots of editions, edition 1, edition 2, edition 75. And every time new editions have more interesting examples. I don't like that they have to ask you to buy a new edition every time. But examples are interesting because I never saw example with a fungus before. A fungus was found on the island. Suppose the percentage of infected trees on the island follow this logistics model. Fungus cannot have infinite growth. There's a limited number of trees to infect. T is measured in weeks. That means someone will keep checking every week and keep measuring how the fungus is spreading. What percentage of trees will be infected 2 weeks from now? And there will be more questions. So this should be recognized in your brain at some point that this is exponential growth model. But since you see fraction here, it should kind of give you an idea. Oh, it looks like a logistic exponential growth model. And yes, you're right. I think I heard someone saying growth model, that there's a negative over here, which also gives away 300 over 3 plus 97 e raised to the minus 0.05 t.
That's not a proper logistic model.
Why?
Because P0, because that would be... Never mind, that's perfect.
Product, yeah.
Because
I knew what you're saying. I knew what you're saying. Good job. So what do you think we should do for the A question A? What percentage of trees will be infected 2 weeks from now?
It's just simplified.
No, just what should I pluck something somewhere? 2 weeks is what? Time. T is 2 weeks, and it matches because time is in weeks, so we don't have to convert. They might ask like for 8 days. You'll have to convert 8 days in 2 weeks. Do you know how to do it? Divide by 7, right? So it'll be 1 point something something. So P at 2 will be 300 over 3 plus 97 e to the minus 0.05 times 2. Honestly, it's fun to notice people being hired to make records of all of this, and students, usually undergraduate students, are hired for money to go and measure all of this. I do know a student who was measuring how wide the trees are, and it took him a week. He measured and he got $2,000 in 1 week, and then there was no limit time, so he just did it faster and got money faster. So students are hired to do this, not necessarily on the island, but even in your own state. Because scientists are busy in the labs, so they like hiring students to be part of the project, and they can walk around a lot.
Nice. You're doing all the cool stuff, so
But you need to learn more STEM stuff to be doing cool stuff, yeah.
no.
That's kind of a good point,
I totally understand.
right? It's approximately 3.3%. So you have to be careful with this. The output has units, and the units of the outputs are percentage. Very interesting. So 3.3% of trees will be infected in 2 weeks, which you can then convert into units, other units, how many trees there are, and so on. Very interesting. B. How long will 75% of the trees get infected?
How long until?
Oh, really? How long will? No, I don't know, I guess.
It would be how long
Until? Yeah. Okay, let's put it. How long until? Good comment. No, I don't know. That's not my English. How long until? No, but there's a will there. Okay, yeah, so I crossed the will. How long until 70% of the trees get infected?
It would either need to be until or will it take for them to get infected.
Oh, yeah, good point.
There's a word missing.
So you guys figure out the English part, I will tell you the math part. That's fair, not my strength.
Sorry.
So, until 75, so that is very realistic, you know. This is when mathematicians give suggestions to CDC. Do you all know what CDC is? I should probably ask this before, right? We give suggestions to the CDC when it's time to close the school, when it's time to announce the state or the whole city should be closed because there's some kind of bacteria in the air, the fungus, the flu actually has different, but pox, for example, escaped, and so on. And it did happen 2 years ago in New York. Some communities started spreading pox, chicken pox, which we thought was under control. They started spreading it, and the whole neighborhood was shut down. Sexual diseases have also recommendations from mathematicians. When it's getting overhand, we invite all the people who were in contact with all the people who get some sexual disease, and then lock them in one location so they don't walk around anymore and, communicate with other people. So we give suggestions to all of this using these models and these numbers. How cool is that? So what is 75? Who knows?
P.
That's your P. Was it P? Yes, P. I'm questioning the name of the variable. P is 75. Don't change the percentages. It is in the percent. 300 is the same. 300 over 3 plus 97 times e raised to the minus 0.05 times 0.5 or just 5? 0.05 t. And now we need to solve for t, which is kind of annoying because it's in the denominator, but it's not as bad as you think. So don't be afraid about that. We need to dig out this t out of the exponential function, out of the denominator. The whole idea, which I teach you, is to isolate this piece. Isolate the exponential, but it's inside of the denominator. Do you remember how to flip the fraction? If you don't, just multiply everything by the denominator. 3 plus 97 e to the minus 0.05 t. You cannot do it if the denominator is 0. But it is not 0, so we are safe. Then it's going to be 75. There's a faster way to solve it, so you go ahead and do it your own way if you know it. This is the slow but reliable way. Times 3 plus 97e raised to the minus 0.05 t equals 300. Now at least it's not in the denominator, and this looks like something we had before. Distribute 75 multiplied by those two guys. 75 times 3. What is that?
We don't need to do that one. We just divide both sides by 75.
Oh, that's actually smart. Let's do that. I like it
That
better.
makes the whole thing way easier.
That's what I would do too. Yeah, let's do that. That is faster. Let's divide by 75. It will be 3 plus 97e minus 0.05t equals 300 over 75. What next would you do? Let's do minus 3 from both sides. It will be 97e to the minus 0.05t. 300 over 75 minus 3. Slowly getting there.
That's
Slow.
just 1.
Really?
300 divided by 75 is 4.
Oh, that's nice. Oh, yeah, that's good. So if this is 4, then this is just 1. 97e minus 0.05 t is just 1. How convenient is that? Divide by 97, and then this ends up to be exactly what we used to have before. That will be 1 over 97. Finally, this is the step when you apply logarithmic function. ln of both sides give you negative 0.05t equals logarithm of the right hand side, no matter what is there. We're lucky to get 1, but don't be afraid if it's not. Something on the right hand side is now inside of the logarithmic function. Finally, solve for t. Divide by whatever that thing is. Any rate or any number still sticking to the t, divide by that number. And the answer will be ln over that number. Minus 0.05 t. So, you will be surprised. It's a negative number. Not really. Logarithmic function can be negative if the input is small. For small inputs, logarithmic function actually below x-axis. So the numerator is negative, denominator is also negative, so the final answer is actually positive. 91.5 units were weeks. So that is less or more than a year? More than a year. How many weeks? In a year? 52. So now approximately, you know, for scientists, they have to wait for a year and a half approximately to have 75% of the trees to get infected. That means they have a year to figure out the problem, or else it might be too late. That's the idea. And that's why it's nice to know. Questions? What do you think? Good job, people. That was very nice chapter, I think. Enjoy your homework, which is due Monday.